In this video, we are going to go over 7.4 maxima and minima using the Lagrange multipliers. Now, this is very similar to Math 121 concept coming from chapter 4.5 and 4.6. We have done absolute maxima and minima and optimization problem in Calc 1. Now, in chapter 7.4, we will still do maximizing and minimizing function, but we are going to be dealing with more than just one variable. We will be working on several variables, x, y, z. So one equation can have three different variables. So it's a little bit complicated. So we need a new method called a Lagrange multiplier. So now we consider a powerful method of solving certain class of maxima minima problem. This method actually was developed from a 18th century French mathematician named Joseph Louis Lagrange, and he come up with a method called Lagrange multiplier. In the method of Lagrange multiplier, we will work with g of xy. So in other words, we have a function xy, but we are coming up with a second function, g of xy, directly and avoid solving equation for one variable in terms of the other, like we did in chapter 4 in Math 121. In addition, the method generalizes the function of arbitrary many variables subject to one or more constraint. So the procedure seems a bit complex because there are 4 steps, as you can see listed on the notes. And this procedure also is written down on the PowerPoint as well. So you can also refer to the PowerPoint notes as well. So the best way is, I'm not going to read through the whole page because it's written right there. I'm going to jump right onto these 3 different examples and then go over these 4 steps so that you feel comfortable going into the procedure 1, 2, 3, 4, rather than for me to just read through and then you get lost. So that's kind of best way to approach. These 3 examples that I'm showing you on this video will give you 3 different scenarios. Number 1 will give you there is possible in a situation where a function cannot give you minimum or maximum. Second example will give you a maximum function value, xy. And then number 3 situation is the function where xyz will give you a minimum value. Okay, so you get a variety different example. Also, I highly recommend, which is also required, go over the last 2 example of the PowerPoint to have a lot of application problem, okay, to complete the homework. Okay, so PowerPoint has 2 application problem. I really want you to go through and look at it. Maximizing or minimizing some area, and there's a Cobb-Douglas function. So both of these are also in part of the homework too. So you can look at the PowerPoint and then see how they approach the problem. Okay, so this is, I'm also going to note to myself, refer chapter 4.5 and 4.6 as a review from Math 121 to help you fully understand 7.4. If you forgot how to minimize or maximize function, it might be a little bit difficult. But if you go back to the old material, it will make a lot more sense. Okay, so just to go over briefly all the notation. This function right over here, this is the Lagrange multiplier function, and particularly the lambda is the Lagrange multiplier. Okay, so here, which is a constant number. Okay, so the lambda is called Lagrange multiplier. Okay. Another thing is in chapter 3, when we did our implicit differentiation, we learned how to take partial derivative. We are given a function and then we were able to derivative in terms of x or terms of y. So this is kind of our partial derivative notation. F of x means you're going to take derivative for x and treat the other variable y and lambda as constant and so forth. So f of y will be take derivative in terms of y and then treat the other remaining x and lambda as constant. And then f of lambda is take derivative for in terms of lambda and treat the other two variable x and y as constant. If you forgot how to take implicit differentiation, review. So I'll write it over here. Review. Chapter 3.5 implicit differentiation. From Math 121 concept. Okay. All right, so let's go through each step and then work on 3 exercises. Let's just jump right onto a problems. Number 1, we have used theorem 1 to explain why no minimum exists. Well, let's go through step 1. Step 1 says, write the problem in the form z is equal to f of xy, and then we are subjecting to g of xy and set that equal to 0. So we have 2 equations. Here's my z of xy, and then here's my subject, which will be my g function. Okay, so let's do that. So step 1, I have f of x comma y as 10x minus 7y. And then this is, we are going to subject, this is my g function, xy, and set that equal to each other. Set that equal to 0. So in other words, I'm going to be subtracting 12 other side, so that will give me equal to 0. So let me write it out. We want to minimize, and then this is our subject function, which is 7x plus 10y minus 12 equal to 0. Because remember, I want that to set it equal to 0. So step 1 is done. Step 2, let's come up with Lagrange multiplier equation, which is step 2, f of x comma y comma lambda is f of xy plus lambda times g of xy from lambda times g of xy. This is just coming straight from the formula right over here highlighted in blue. So that means I'm going to be plugging in my f of x function, also known as z function here. And then remember the g function that I come up with and set it equal to 0, I'm going to plug it in. So I'm going to take my f function, plug it here, my g function, this whole thing right over here. So let me highlight it so you guys can see clearly. Here's my f of x function. You can see that right there. And then my g of x function right there. So my function will look like f of x comma y comma delta lambda, my Lagrange multiplier equation. 10x minus 7y is my f of xy. Lambda times 7x plus 10y minus 12. Okay, just literally plug it in into the equation right there. Okay. I'm going to do a little bit of a math and distribute these lambda, okay, and then put it into a nice single formula without the parentheses. So after distributing, I have 10x minus 7y plus 7x lambda, 10y lambda minus 12 lambda. Part 2, finish. Step 3. Step 3 says I have to set a function. I have to take a partial derivative of this function in terms of 3 times x, in terms of y, in terms of lambda, like an implicit differentiation, and then set each equation equal to 0. Let's recall, when I say f of subscript x, I'm going to only look at the x term and treat all these y and lambda constant. So for example, if I'm looking at f of x, my partial derivative, x comma y comma lambda, I'm looking at this right over here. Anything that is not x, I'm treating as a constant. So this will be like a constant. This will be kind of like 7 lambda x, constant. So really, I need to I need to focus on these two terms. This is the x term and this is the x term, right? For this. So 10x, if you take the derivative of a 10x in respect to x, it will be just 10, right? Derivative of 10x is 10. The middle term, because y and lambda is constant, this disappear. This also disappear. This also disappear. I end up having 2 terms. Think about this. This will be 7 constant, 7 times some number. So 7 lambda x will be my term. If you take the derivative, only 7 lambda will be surviving, right? Let's do one with the f of y. This time, my variable is y. Okay, y. So I'm only focusing on the y terms, and then remaining will be constant. So negative 7y, that will be negative 7. 10 lambda y will give me 10 lambda, and then other one will be constant. Last one will be, I'm going to have a lambda. Lambda will be my variable, and then x and y will be constant. Oops, I think I made a mistake. This is not a z. Should be lambda. So here, let's do this. Lambda will be constant. So anything dealing with the lambda, so it will be this one here, and then this one here will be my terms that I need to differentiate. Other two will be just constant. So this right over here, I'm going to have, remember, lambda is the variable. These are constants, so I have 7x for the first one. So you have to treat like x as a constant. Same thing here. Lambda is the variable, so this will be my constant, so 10y. Lambda is my variable, so negative 12 will be my derivative term. Okay. Now, once you differentiate, you will set each function equal to 0 and solve for lambda. Okay. However, now here's the problem. This is why the minimum does not exist. When I set this f of x equal to 0 and then f of y equal to 0, you see that x and y term disappear, only lambda. So I cannot use x and then y. X is not existing because x variable disappears. Same thing, y does not exist. So I cannot plug it into this equation. So therefore, there's no critical value. I cannot find the critical value because x variable is gone, y variable is gone. You know there's a 3 equation, so I need to have 3 unknowns, but I don't have it. So therefore, we cannot get a nice order pair. So this is the reason why the no minimum exists, because I cannot solve x, y, and then lambda. So therefore, f of x equals 0 and f of y equals 0 have no simultaneous solution. So no minima exist. Okay, and that's it. So first case is no minima. Second and third case, one of them I'm going to show you there is a minima, and then other one we have a maxima. So you have 3 different variety. Okay. So one example, the next example is maximizing with the 2 variable. Third example, I switch to minimizing and I have 3 variable. 3 variable works exactly same too. Theorem 2, anything with the 3 variable, you just add one more equation, so 4 equation, but the process will be is still the same, 4-step process, just longer. Okay, so let's begin with something simple, minimizing, and this is 2 variable x, y. So let's begin with step 1, rewriting the problem. So step 1 says we want to maximize the function f of x comma y 9xy subject to, so this is your g of x, y equal to 0. In other words, I have to set that equation 0 by moving 6 on the other side. Subject to 2x plus 2y minus 6 equals 0. Step 2. We just did it. Step 2. What are we going to do? We are going to write our Lagrange multiplier function by maximizing or minimizing function here, multiply with the lambda, and then subject equation on the last term. So the function is f of x, y lambda equal to f of xy plus lambda times g of xy function. So in other words, this right over here will be my first term. My second term will be this function here. So let's plug it in. F of xy lambda equals 9xy plus lambda times 2x plus 2y minus 6. Distributing lambda to get rid of the parentheses, I'm going to have 9xy plus lambda, 2x lambda, 2y lambda minus 6 lambda. So that's step 2. Step 3 says I need to take a partial derivative, and each partial derivative function will be set it equal to 0. So let's do that. Again, f of x means take derivative in terms of y, treat other variable constant. F of y means take derivative in terms of y and treat other two variable constant. Last one, lambda is your variable that you want to take the derivative, and then other two will be constant. So step 3. So f of x, so I'm looking at this equation over here and take the derivative in terms of x. So the so I am particularly looking at the x one with the x variable, this one and this one. Other two will be disappearing because they're constant. 9x, remember y is also constant, so in a sense you have a 9yx. So the derivative for the first term is 9y. Second term, again, that's one thing you need to differentiate because this has an x variable. So 2 lambda x is your constant. So plus 2 lambda. Set that equal to 0. Okay. Let's do it one more time. F of y. This time, y is your variable. X and lambda is a constant. So same thing happens. First term, have a y involved. This one disappears, this one disappears. So it looks like first and then third term. 9xy, remember x is a constant this time. So 9 times constant, so constant. Something constant times y, so 9y is my derivative. 9x. Here, 2 lambda is my constant. F of lambda, x, y, z. This time I'm looking for lambda term. So first term disappear because they're all constant. Looks like I'm going to have to differentiate these 3 terms. Lambda is variable, so 2x is a constant, so first derivative term will be 2x. Second one will be lambda is my variable, so 2y will be your constant. And then lambda is your variable, so it's -6. Set it equal to 0. Okay. Now, looks like we will have a maximum this time because I can solve x and y here and plug it in to solve lambda. Right? So let's do that. So from this, let me use different color. So we have 9y plus 2 lambda equals 0. Subtract 2 lambda equal to 0. 9y equals, made a mistake. Minus 2 lambda, right? So I have 9y equals -2 lambda divided by 9. Y ended up being -2 lambda 9. Okay. Similarly, I can solve x here. So I have 9x plus 2 lambda equals 0. Subtract 2 lambda, divided by 9. X end up being -2 lambda over 9. What am I going to do? I'm going to plug it in x here and then y into the equation. Okay. And solve for lambda. So my equation now will look like 2 times x, which is negative, let me use red. So it's a continuing step 3. So 2 times x, which is -2 lambda over 9, plus 2 times y, negative 2 lambda over 9 minus 6 equals 0. Distributing negative 4 lambda over 9. Distributing negative 4 lambda over 9 minus 6 equals 0. We're solving for lambda. That's my unknown. These two I can combine. Negative 8 lambda over 9 minus 6 equals 0. Add 6. I have negative 8 lambda over 9 equals 6. Multiply negative 9 over 8 to solve for lambda. Lambda is equal to, let's see, negative 54 over 8. Okay, so negative 54 over 8 is it's exactly negative 6.75. So lambda end up being negative 6.75. Okay, so that's step 3. Step 3, we set it equal to each other and then solve for lambda. That's your critical point. X, Y, lambda is the only critical point. So let's keep going. So here's my X, here's my Y, here's my lambda value. So X, Y, lambda. That's your order pair for the critical value. I'm going to add another page. Okay. So step 4. My critical value x, y, lambda will be, from the previous page, we got x as negative 2 lambda over 9, y as a negative 2 lambda over 9. Lambda was negative 6.75. So my x value will be negative 2 times negative 6.75 over 9. My y value will be negative 2 times negative 6.75 over 9. Lambda is just negative 6.75. So getting all this into a decimal value, so 6.75 times 2 divided by 9. X coordinate, I get 1.5. So y is also 1.5, negative 6.75. Okay. So since 1.5, 1.5, negative 6.75 is the only critical point of f. So what does step 4 says? So that is the only critical point. We assume that x comma y will always produce solution to the problem. So that's it. So once you find the critical value, that x and y component is your solution. So the point 1,5, 1,5 will result in the maximum, because we are maximizing value of the function. Okay? So once it looks very long, and then all those variable looks a little bit kind of like intimidating at first, but once you actually do it with the problem, it's not too bad. Very similar to our minimum maximizing with the one variable in the past. Okay? So one more problem together. This time we are going to minimize one with the 3 variables, x, y, z. So it looks like I'm going to be using theorem number 2 with the 3 variables. Now coming up with 4 different equations, but the process will be still the same. I'm going to do 4 steps. So my first step is to rearrange the problem, write the problem in the form x comma y equals z, and then subject to set the function equal to 0, the standard form. So this one is already there. Second one, I have to set the equation equal to 0. So move this one to the other side. Okay. Step 1, rewriting. We want to minimize this time. F of x comma y comma z as x squared plus 2y squared plus z squared. And then we are subjecting to 2x minus 2y plus 3z, add 21 equal to 0. I'm adding to move to the other side. Now let's come up with our Lagrange multiplier equation, which is highlighted in blue. Okay. So I'm going to use the maximizing function for the first term and then subject function on the second one, multiply with our lambda. Step 2. So my f of now x, y, z lambda, because there's 3 variables, plus the lambda. So I'm going to have f of x, y, z plus lambda times g of x, y, z. So this will be my x, y, z function here, and this will be my g function right over here. So x squared plus 2y squared plus z squared plus lambda times 2x minus 2y plus 3z plus 21. I'm going to distribute all the lambda. So my final equation after distributing will look like x squared plus 2y squared plus z squared plus 2x lambda minus 2y lambda plus 3z lambda plus 21 lambda. Okay. Step 3 is taking the derivative, partial derivative. This time I have to do 4 because I have more variable introduced and then set each of them equal to 0. But same thing. I'm going to treat the last one z as a variable and then remaining one as a constant. So let's try the first one. F of subscript x, taking the derivative in terms of x comma y comma z lambda. So looking at this right over here, and then I'm looking at this function here. I'm going to look at the terms with the x term, right? And then other ones will be just constants. So this disappears, this disappears, this disappears, this disappear, this disappear. So looks like I'm going to end up having only 2 terms. First term derivative and then fourth term derivative. X squared, if you take the derivative of x squared, that will be 2x. Now this one, 2 lambda x. So the constant is 2 lambda. So it looks very simple. I'm going to end up having, right, 2x plus 2 lambda equal 0. Okay. Now let's do f of partial derivative y. This time I'm only paying attention to the y term. So this is a constant, this is a constant, this will be constant, this will be constant, this will be constant. So I really have to pay attention to the second term and then the 5th term. 2y squared, if you take the derivative, that will be 4y. This one over here will be 2 lambda, but negative. So I have 4y minus 2 lambda, set it equal to 0. F of z is your variable, other one will be constant, so I just have to pay attention to the z term. Constant, so constant is a 0 derivative, so this one also disappear. This one will be one that I need to take the derivative. This disappear because it's a constant, this one. These two are the only one that I need to differentiate. Z squared, if you take the derivative, it's 2z. This right over here will be 3 lambda. So z squared, so 2z plus 3 lambda equals 0. Last one is a lambda, so x, y, z term is constant, only the lambda is the variable. So looks like I'm going to have this one disappear, this one disappear, this one disappear. And then, okay, so the last 4 will be my term that I need to differentiate. Right, so this is the term that I need to differentiate. So let's start with the first one. This right over here will give you 2x. Second term will give you, remember lambda is the variable, so negative 2y. This one over here plus 3z. And then last one, this is the variable, so constant 21, set it equal to 0. Okay. All right, let's start solving x, y, z. Okay, from here, x, y, z, whatever x, y, z we have, I'm going to take this and plug it into here to find the lambda. Okay, so let's see. From the first one, I have 2x plus 2 lambda equals 0, 4y minus 2 lambda equals 0, and then we have 2z plus 3 lambda equals 0. So subtract 2 lambda by 2. Looks like x equals negative lambda. Add 2x lambda, add 2 lambda. 4y equals 2 lambda divided by 4. I have y equals 1/2 lambda. And then subtracting 3 lambda, I have 2z equals negative 3 lambda divided by 2. Z is equal to negative 3 over 2 lambda. I'm going to plug it in, x, y, z, all these into this equation x, y, z, and then solve for lambda. Okay, I'll do that on the next page. So we have 2 times, it was 2x from the previous page, 2y plus 3z plus 21. After plug it in, I have 2 times x was negative lambda, y was half, or you can think of it as 0.5 lambda. Z will be negative 1.5 lambda. Okay. Just like to have a decimal rather than a fraction. So plug it in, negative 2 times y was a 0.5 lambda. Z was a negative 1.5 lambda plus 21 equal to 0. So let's see, this will be negative 2 lambda. This over here will be negative 2 times 0.5, negative 1 lambda 3 times negative 1.5 will give you negative 4.5 lambda plus 21 equal to 0. Adding all the lambdas, negative 2 minus 1 minus 4.5, I get negative 7.5 lambda plus 21 equals 0. Let's keep going to solve for lambda. Minus 21, negative 7.5 lambda equal negative 21 divided by negative 7.5 lambda. I'm getting in a decimal, negative 21 divided by negative 7.5, 2.8. 2.8. Okay, so I know my lambda. So let's go back, and I'm gonna go back and copy all this. X, remember, I need to plug it in, all those lambda to get X, Y, Z. Okay, so X will be, plug it in, X times negative 2.8, that's lambda, that's X. Y will be 0.5 times lambda, which is 2.8. So y end up being 0.5 times 2.8, 1.4. Z is negative 1.5 times 2.8, negative 1.5 times 2.8, which is negative 4.2. Okay. Plus the lambda. So my order pair, my critical value will look like this time x, y, z lambda, which is negative 2.8, 1.4, negative 4.2, comma, my lambda 2.8 is the only critical value critical point of f. So only x, y, z will be my final answer. Negative 2.8, 1.4, negative 4.2 will result minimum value of the function. Okay, so I'm looking for this one. This will be your final answer. All right, so we have 3 different situations. We cover when we can have a minimum, when we have maximum, and then no minimum or maximum. There are a couple application problems, so please look at those PowerPoints for more variety examples and then application problem as well. That's it for section 7.4. I will see you guys in the next video.